Today we're going to talk about epidemiology. Last week we learned that the mission of public health was to promote physical and mental health and prevent disease, injury, and disability. And we looked at this little flow chart that kind of goes through the process of what you do, and research being in the center is kind of the epidemiology part. The process we talk about is to first you identify or detect a problem. A problem comes to your attention. In this case, it's going to be myopia. And we want to know, is it a problem? How frequently? What's its prevalence? How many people in the world are myopic of various ages? What is the incidence rate? How many people acquire myopia for the first time each year? We want to determine its cause as best we can, and that requires a number of studies like longitudinal studies, randomized controlled trials, and other kinds of studies. Animal studies kind of can apply here as well in terms of understanding the nature of how myopia develops. And then we want to use this information to motivate and develop an evidence-based public health policy. Now, normally we think of public health as, or a lot of times we think of public health as access to care or free clinics, but it's more than that. And in our case of vision, the federal goals under Healthy People 2020, and I'm sure you've encountered this concept before, there are a couple of things related to the topic we wish to address today, which is myopia, and increase the proportion of preschool children who have vision screening from 40 to 44%. So we want to screen more kids, detect more vision problems, catch them early. There are other goals here, but again, we're going to focus on myopia. And so a second one that is kind of important is to reduce visual impairment due to uncorrected refractive error. Now, what is the data that they use to come up with this goal? They go out and they do a study by the National Health and Nutrition Examination Survey. That's conducted by the Centers for Disease Control and Prevention. This survey is actually a live survey. They go out, knock on doors, get people to have a little examination van, and they ask extensive questions about all sorts of information about all forms of health, mental health, vision, hearing, just everything. They have a little van with like our eye van, where they go in and they have exam rooms and they test people. This is a very comprehensive, very large, and very well sampled program that gathers a representative sample of the United States. And they get, as a result, they have pretty good estimates. You can see in 1999 to 2002, over that period of time, they had about, 118 cases of refractive error per 1,000 people in the population. This has increased to around 136. 136 patients, or myopics, or refractive errors rather, per 1,000 people in the population in 2005, 2008. And their goal is to bring it down to 122 by 2020. Now, some of the things this means that right now there are about 35 million people in the United States have uncorrected refractive error. You think there's a market out there for your services? It looks like it, just if you wanted to do glasses. So how can we reduce uncorrected refractive error? Well, we can make people more aware that they could have a problem, so people seek help. Another thing that we could do is get more access to care to get corrected. The Affordable Care Act had some provisions to kind of promote that type of policy. The AOA comes up with public health policies to kind of promote that. And the third way is to not have refractive error in the first place. If you think about it, let's just take the case of myopia. So a kid comes into your office, it turns out he is nearsighted, you give him glasses, and then he goes home. Well, what happens with those glasses? It looks like there's pretty strong evidence that the single vision lenses that you give him or her creates a hyperopic peripheral field that actually promotes eye growth. So kid can't really see very well. You make him see well, but in the process you tell his eye to grow more so that he needs a prescription next year. In a way, it's a pretty good marketing idea, but may not be the best. So what if you want to fix his myopia? Well, if you go to the contact lens department, Pat Caroline can give you a prescription for your patient that will have ortho-K lenses, and he can actually stop the progression of myopia. A lot of the current states of orthokeratography allow you to slow it down maybe 0.5%, but he's got a way of doing it so that it does really better than that. And we have the data to show that. But ortho-K is kind of an expensive alternative that is not accessible by many people. Also, to be most effective and to actually reverse myopia, I think that you have to get the child much earlier. And we don't like doing overnight on young kids, though the contact lens group is working on that as well, to keep it from being overnight. So another thing you could do is give glasses that don't have that peripheral refraction problem. Again, a more expensive alternative, but it is not long before, not too many years out, and you really need to keep up with the literature on this, that is going to be bad practice, if not malpractice, to prescribe the same single vision lenses to children that you do now, because myopia can be at least slowed and not aggravated with single vision lenses, and maybe even fixed if you catch it early enough. But it's hard to capture all these people all around the world, and even in the United States, those 35 million or some subset of them are not going to see their eye doctor at an optimal time. And so are there policies and is there evidence that we can prevent myopia in the first place? Now, I'm not here to suggest we all go out of business by correcting refractive error, and I don't think that's going to be possible. But it is possible maybe to reduce the numbers or slow it down or something to kind of improve upon that. And we're going to look at some of the data about that in a few minutes. But first, we want to expand on this idea. We've seen how many people have unrefracted or uncorrected refractive error. How about just myopia itself? So there's a paper by Brian Holden out of the Brian Holden Institute in Australia, and he looked at global prevalence of myopia and high myopia and trends from 2000 projecting through 2050. And he did a systematic review and meta-analysis, and he looked at a lot of studies, about 145, covering 2 million participants, and estimated that the world has 1,406 million people with myopia, 22.9% of the world population, and 163 million people with high myopia. Now, they also predict from their studies that they looked at that there will be 4,758 million people with myopia, or about 50% of the world population by 2050, and 938, almost a billion people with high myopia. High myopia is having diopters less than 5 diopters. So that's a lot of people. And some people would call this an epidemic. So epidemiology, the idea is to look and study epidemics and look at the causes. Here we see a graph that shows the annual increase in regular myopia and high myopia over the years from 2000 to 2050. So one question is, should we even try to prevent myopia? I mean, what's the big deal? You can fix a person with a -6 refractive error. It gives lots of business to optometrists, job security. But if you think in terms of, I think maybe the most convincing thing to try and slow people down is this concept of the increase in high myopia. Even if you can fix all these people, if you saw them in the first place, the high myopes tend to have serious disease, can get serious disease. The retinal detachments or the myopic retinopathy or whatever all the diseases are related to high myopia. Just simple correction is a fixable thing, but we're spending billions each year on this condition. So when we talk about the CDC's definition of an epidemic, it's the occurrence of more cases of disease than expected in a given area or among a specific group. And we have seen that there's more cases of myopia each year than expected because it's growing so fast. You would expect it to be, why is it growing so fast? And we can also determine that there's a lot more people with myopia if they're Asian. And China and other places in Asia have a very high incidence of myopia. But we're growing here in the United States as well and in Canada. Now, epidemiology is the study of the distributions, frequency patterns, and determinants, causes, and risk factors of health-related states and events, not just diseases in specific populations. And so our question is, what is the cause? Before we can figure out what policies to do, I mean, we can have policies and do healthcare's ACA kind of things to get people into care and to fix it. But what can we do to prevent it? What is the bug out there that's creating myopia? So I'm going to talk about a few studies here. The first one was in 2007, and actually there was one earlier. I believe it was 1993, 1995. There was a cross-sectional study that showed that outdoor activity may be related to the growth of myopia. But pretty much nobody paid any attention to it. And to be honest with you, I was working with this group in 2005 and 6 when they were putting together this paper. And this group, Carla Zadnik's group and Don Moody, they would have Monday meetings at noon where they'd talk about the data and the myopia study. And there was originally the Orinda longitudinal study of myopia, and that was in California. And then it was expanded to CLEAR, which looked at ethnicity and was over many other parts. But they would sign kids up and then follow them over the years. Well, they came to me and they said, you know, we have two kinds of data. We have the exam data, where we look at people and we look at the kids. They come in, they're like in somewhere between the 1st and 5th grade when they sign up. Most of them are 3rd graders. They come in, they get an exam, and they look at everything. Only in one eye. I don't know for the life of me why they only looked at one eye. That seemed to be one of the dumbest things. So they're not doing any binocular stuff. So just the right eye, of course. And they collected everything with that. They dilated, they got they got refractive error, they got axial length and vitreous chamber length. Actually, they got axial length, anterior chamber length, lens thickness, and they subtracted to get vitreous chamber depth. So they got all these measures, and that was by examining the kid. Then they looked at, or they gave the parents a survey, and they asked the parents, does the mom wear glasses? Does the dad wear glasses? What do you wear glasses for? What's your ethnicity? What's everybody's ages? They ask questions like, then they ask activity questions with the kids. So how many hours a week does your child study? How much does he just read for fun? How much time is spent in front of a computer? How much time does he watch TV? How much time does he go outside? Now, the outside one it would have been nice if they just said play outside or something like that. They actually added sports, which probably, they said how much time does he spend in outdoor sports, as though the only reason a kid would go outside is to be in some sort of sports activity. I guess they were expecting a lot of soccer moms. But anyway, they asked that question, and that was ended up being their proxy for these studies on the amount of hours per week in the outdoors. Now, one of the things that they did was they would, in this first study, they just looked at at the activities, and they looked at rather than so much controlling for the other stuff. I think they did that a little bit, but not so much by the individual parameters. They just looked at the average number of hours per week spent in activities for 3rd graders. And they had followed these kids for a long time, so when they were in 3rd grade, They only looked at kids that were not myopic. But then they divided the kids into two groups, kids that would become myopic sometime during the study and kids that were not myopic at some time in the future during the study. So they were able to look, because this was a longitudinal study, they were able to go back in the third grade, look at how much activity they did, and then compare the myopes to the non-myopes. What they found was that the only variable that was significant was the hours of sports and outdoor activity. There was no significant effect of near work. And that was not what anybody was expecting. Everybody expected that near work would be the problem and outdoor activity would not. Now, I remember sitting at the table thinking, well, this is the dumbest thing I've ever heard. Because what is the mechanism for being outside? You know, there was no known mechanism or no thought about what the mechanism could be. There was a clear mechanism, or supposedly a clear mechanism, when you were inside, your nose in a book or all sorts of things, and just eye strain and all sorts of things. But outside, it didn't make any sense. And so while in this discussion, we're not going to go over the argument for why outside is important. We could have a lecture on the chemical cascade of what happens when a light beam hits the eye and how it goes through and tells the eye to stop growing. But let's look for a minute to see how people score these. For example, in this one, they had the hours were 11 hours and 11.65 for the non-myopic kid of being outside versus 8 hours for the myopic child, future myope. So they're not myopic yet. This is their history. And you get an odds ratio of 0.91. But if we subtract, remember effect size. Remember 11.65 minus 7.98 divided by the standard deviation gives you an effect size of 0.52. That difference was 0.001. Now, it's a really small p-value because there's a lot of subjects. But that effect size, if you'll remember from evidence-based, we talked about 0.5 being a size which can probably be noticed by a patient. So a kid would notice the difference between being out for 11.5 hours in a week versus 8. So the effect size for reading hours, I guess I don't have the means right here, but the effect size was 0.16. And that's pretty small, and the p-value wasn't significant even for the sample size that they had. Now we notice here that there are odds ratios, and one of the objectives for this week is to know about odds ratios. Now I think we probably already covered this in evidence-based, so I just wanted to just do a brief review. I am not going to have us work out or have you work out any problems with this. I'm just going to show you what we have. The above is not myopia data. It is data, real data, but it's not from myopes and activities. But consider that we had 1,288 children that were not myopic and 125 that were. And that 701 had little outdoor activity and 712 had lots. So if we were going to calculate the risk of becoming myopic with little outdoor activity, you would divide 89 by 701 and get a risk of 0.13. If you were myopic and had lots of activity, your risk of becoming myopic was 36 divided by 712, or 0.05. And the relative risk is little activity divided by lots of activity risk, and you get 0.40. Now, in most of these studies, they use logistic regression to come up with the odds ratios. And we'll talk about this a little bit more in a minute, but basically, the logistic regression gives you the odds ratio, not the relative risk. And so we're going to talk a little bit about how that odds ratio is calculated. So in an odds ratio, you take 89, the number of myopes, but you don't have the grand total of 701 to work with. You have the number that are not myopic. So 89 over 612 is an odds of 15, 0.15. And if you have lots of activity, it's 36 divided by 676, or 0.05. And then the odds ratio is 0.05 divided by 0.15, or 0.375. So I set it in reverse over here, but the point here is that if you put the lots of activity on top, then this fraction is smaller than this fraction, and so your number, your odds, is going to be less than 1. Works the same way over here. Now, this odds is the odds ratio based on what's your, what percent of people are going to get myopia. And if you have lots of activity, it's less than 1. It's 0.37. The reciprocal of that is 3 something, or around 3. It'd be 3 times as likely if you didn't have very much activity. Odds ratios, if you'll recall, this is a slide you've seen before but probably don't remember, mostly anyway, it's the same. Odds ratios estimate relative risk. An odds ratio or relative risk of 1 means there's no effect. There's no effective activity, say, of being outside or near work. The odds ratio always overestimates the relative risk. So if we look back here, 0.37, now I said it overestimates it, but 3.7 for the odds ratio is further away from 1 than 0.4. That's why we say it overestimates it. So you have to be a little careful. The other thing is that overestimation is minimal when the prevalence of the disease is less than 10%. Again, in this case, you can see how these numbers are kind of smallish, and we're using this as the denominator instead of the total. So when you add these smallish numbers to these other numbers, you're getting a number that's, in the neighborhood of 7. So the closer this is to this, the more accurate your odds ratio will be in terms of estimating relative risk. Now, if you think about myopia prevalence is pretty high. It's definitely over 10%. So generally speaking, you get a pretty good estimate with odds ratio and things like AMD and glaucoma, but not so good with myopia. So we have to be a little careful when we look at the odds ratios with myopia. Now the next thing we can look at, in their paper they said multiple logistic regressions were performed for statistically significant variables from the univariate models. Optimally, relative risk would be used to characterize the risk of myopia, But given the logistic analysis used in this study, we present odds ratios with accompanying 95% confidence intervals. They don't mention that it's a bad estimate, but anyway, we know it is. We know that it's not, we know that it's an overestimate. So if you remember, if you recall linear regression, y equals a plus bx, y is a continuous variable. In logistic regression, we're talking about the y being myopia or not myopic. And that gives a funny thing. And in order to make make myopia a linear variable, we have the probability of being myopic divided by 1 minus the probability of being myopic. And we take the natural log of that, and that's called a logit. This converts a funny looking squiggly line into a straight line and allows us to solve for b. In the case of our myopia, we have the natural log of the probability of being myopic over 1 minus the probability of being myopic equals a plus b times hours of activity. And if we exponentiate this b coefficient, take e to the b, it yields the odds ratio. And again, if b equals 0, if this coefficient is 0, then then exponentiated equals 1. In other words, the odds ratio is 1 and has no, that means that hours of activity have no effect. Now, in our case, the odds ratio 0.91 means a 9% reduction for 1 hour increase per week of outdoor activity. Now, if we remember correctly, that's not a very big effect. 9% reduction is not very big. And we said we had a pretty good size reduction of half a standard deviation, effect size 0.5. That's a reasonable size difference, but this is little. But it's a reduction for a 1 hour increase. In order to determine what the true odds ratio is of activities in general effect on becoming myopic or non-myopic, you would multiply this coefficient by a number of hours of activity. And in case that we had up above, it was maybe 3 hours difference. You'd multiply it times 3, exponentiate that, and you would get a much better looking, a smaller number here, and it would suggest that the odds ratio is smaller. So in their paper, when they wrote this, they first of all overestimated their effect. That 9.1 is probably not as much as a 9% reduction, but they didn't tell you that you could multiply this a little bit more by 1 hour, so it's actually a bigger reduction than it looks like. So, you know, that group is great, and they wrote that paper obviously without my assistance. Just kidding. But anyway, it's a pretty decent. It turned out to be a pretty decent effect, and they gave the mean hours, which is a good way of presenting that instead of the odds ratio. It just makes more sense since hours are continuous numbers, and this odds ratio is implying a binary event. One thing we could do is, if we had the regression equation, we could figure that out, and that would give us the probability at which the cutoff, how much exercise you would need each week to prevent myopia. Right at the point where if you exercise more, you would be protected, exercise a little less, you would, by this model. Of course, that doesn't completely apply. In the real world, there's variability in there as well. I am going to take a little break now, and you can take a break, and we'll come back and continue on some of the studies leading up to making the case for activity in as a cause or as a likely cause for the development, for lack of activity, for the lack of um, activity as a protective agent for myopia.